Okay, it looks like quite a few people have made it here from the other tutorial. So I'll
Mhm.
go ahead um, and introduce you all. So this is the tutorial for Open Fabrics Interface Libfabric. The speakers for this tutorial are Rajalaxmi, Angadi, and Juee, Himalbhai, Desai. And a brief introduction.
Yeah.
So Rajalaxmi is a middleware engineering manager at Intel Corporation, leading Libfabric software production team. She has 17 plus years of industry experience in various capacities, ranging from design development to management. She has been heavily involved in the development of schemas and mockups for SNIA Swordfish in the Scalable Storage Management Technical Working Group. She has co-authored multiple technical proposals and contributed to the NVM Express Consortium. She is a key contributor of Distributed Endpoint Manager. She is also a core team member of Technical Women at Intel Network Cross-Site Committee, focusing on the EMEA region. Prior to Intel, she worked with a stealth mode startup, Semantic Software, Computational Research Lab, Hewlett Packard, and Flextronics. She holds a master's in information technology and management and a bachelor's in computer science and engineering. And Juee is a middleware development engineer at Intel Corporation, working under Rajalaxmi to support Libfabric's software productization. She has 2.5 years of industry experience working in computer networking. She has been with Intel developing and testing Libfabric components for the past 10 months. Prior to Intel, she was with Pluribus Networks, working on physical layer technologies. She holds an MS in electrical engineering from USC and a BE in electronics and communication. And so thank you. We look forward to your tutorial. I just want to note that I need to step out to go pick up my son from daycare. So I will not be here to moderate questions, but they will be in the chat here. And I will also put one more link to the Slack channel as well.
Okay, thank you. Thank you, Amanda, for a very good introduction. Hello all, good evening, good afternoon, from wherever you are. This is Rajalaxmi, and today we are going to be presenting a tutorial with OFI Libfabric. We also did a tutorial last year, but last year we spoke mostly about different APIs within the Libfabric and how are the different parameters that could be used, and we went through a brief architecture of Libfabric as well. But this time we want to do a precursor for that. We want to go from bottom up as to how do you start with Libfabric. Next. So today we will be talking about the building blocks for programming communication software, and we will see what are the challenging or changing arenas of hardware and software, and why we need Libfabric. We'll see a brief outline of architectural outline of Libfabric. Then we'll see the different grouping of the APIs, and then we will dive into examples, and we will be showing GPU data transfer examples. So that will be more interesting to the crowd here. Next. So when we talk about the building blocks of programming communication software, the first question that comes to my mind is what does it take to program communication software? And that too, when we have to program it for high performance computing or AI. So where it mostly involves transferring data from nodes to nodes or across the nodes or with the internode or intranode. I should thank Dr. Panda and his team for introducing so many topics in the high performance computing and different complexities that are involved over there. So even before programming those complex communication software, we should see where does it start from. It basically trickles down to how do we write a simple program to transfer the data, wherein one program can send and receive data from another program. So the traditional way that we have learned in the schools for doing this is socket programming, which involves a client and server. We create sockets, we send data and receive data from there. The connections could be connection oriented, or it could be connectionless, like the UDP. But we are not going to go into those details here because we are going to be talking about the important thing, Libfabric here. So, but the bottom line is the communication software program is very complex, especially if we have to write those programs for HPC and AI. Also, when it involves a lot of different type of hardware underneath, and also when there are like so many middleware libraries involved in there. So next. So before we dive into that, let's see a simple socket program for transferring data from a client and a server. This is a very basic thing. Everybody must have learned this in the school. There is a server program which creates a TCP socket. There is a bind function which binds it with an address and the port. It listens on that port and then waits for any connections. On the client side, it creates a socket, then it connects to that server. Then there is a data exchange through this send and receive APIs. And then they close the sockets, and then that's the end of that program. But we see that here they are transferring through the TCP sockets, and most likely this is going to be on an Ethernet connection. If these two programs are running on two different nodes, then they are talking through the Ethernet fabric there. Next. So we saw that we saw an example with a simple client and server program talking to each other, transferring data through the Ethernet fabric. Imagine if you have to have a high performance computing application, and like you might have seen in the previous presentations, it involves like hundreds and thousands of nodes, and those nodes are connected with different type of fabrics. So, and these days we not only have nodes with CPUs, we have all kind of compute elements like CPUs, GPUs, XPUs, DPUs, and IPUs and whatnot. You must have heard from Dr. Panda and team there. And all of these are also connected with different kind of fabrics. It could be Ethernet, it could be InfiniBand, it could be fiber channel, connecting nodes to nodes. And now we have GPUs sitting inside the node, and those GPUs also talk with the interconnects like XE-Link or NVLink. And the situation becomes more complex when there are switches involved in there. Suppose if you have to connect like hundreds of nodes, you cannot connect them back to back. You have to go through a switch. Similarly, within the GPUs also, now there are like concepts of the link switches there. So like, for example, I can say NVIDIA's NV switch there. And this is like the hardware part of the story. Now, if we talk about the software side, there are like different middleware libraries. Like we have Intel MPI, we have MWAPitch, we have MPitch, we have different type of libraries. We have one CCL or CCL, like there is Habana CCL, there is NCCL. And then there are applications like HPC applications like weather for more modeling, or it could be LinPack, or it could be any other application. It could be any other AI application as well, which is making use of all of this software stack plus the hardware. So, so things become complex, and programming with all of these variety of software and hardware becomes very complex. So we need a common interface to bridge this gap between the hardware and the software. Next. So yes, Libfabric comes to the rescue. But what is Libfabric? So Libfabric is nothing but it's an open interface that focuses on exporting and tightly mapping the underlying fabrics communication semantic services to the applications on top. You see there is the Libfabric in the dark blue blocks there. And then below there is hardware, which could be like all those variety of hardware that we saw. And then the application middleware could be all those variety of applications that I mentioned. So it kind of sits in between to bridge the gap. So it is designed with a focus on performance and scalability requirements, and it also enables the developers to use the common API that could support various fabric stack underneath. We also saw in the previous presentations the architecture diagram of how Libfabric can bridge this gap. We saw a few examples there, and I'm going to also show in my next slides as well. But the key component of these are like the interface of the Libfabric is the interface that's facing towards the application so that applications can get in. Application developers will find it easy to use that one common API. And then it can hide all the um, fabric specific APIs which are below it, and that makes the developer's life easy. And it is also it can also be performant as compared to like 1:1. It basically makes it easier for the portability purpose. So it's also good to know that Libfabric is also supported on different operating systems, different versions of operating systems as well. Next. So, like you see, like I told, like what is Libfabric? Now, why we need Libfabric here? Juee, can you do next? So we see that there are like different variety of hardware at the bottom. We have switch, we have switch network, we have different kind of network interface cards, we have Ethernet cards, we have InfiniBand cards, we have compute elements, GPU, and their own fabrics. And we have data streaming application engines as well. So when we have all of these at the bottom, so it all of these also have their corresponding subsystems in the kernel as well. Next. And then on the top, we have middlewares like MPI, CCL, and SHMEM that's sitting on top. And you see that there's a Libfabric that's sitting in between to bridge the gap between these two. So like you see, there is a socket provider for socket subsystem for Ethernet kind of interface. There is RDMA provider that is that will cover verbs, rocker type of like the RDMA based interfaces. There is GPU provider that can cater to the GPU subsystems. And then there is a shared memory semantic. So when we saw that first example of a simple socket program, imagine that you have to write that simple socket program wherein the fabric would be the Ethernet software stack. And then imagine if your software, if your hardware changes to an InfiniBand, then you have to write a separate program with all of those separate APIs. And imagine if you have to write for a shared memory provider, or like if you have to write a program that utilizes a shared memory, then that whole program has to be rewritten. Next. So that is why I think the Libfabric provides one common abstraction interfaces that can bridge this gap. If we have to simply translate that simple socket program into a Libfabric program, then you see there are like similar APIs. Like we have FI get info to get the underlying fabric information and properties. There is FI fabric and FI domain, which kind of creates, which kind of defines the interface. And then there is a endpoint, which is equivalent to the socket endpoint, and there is a bind, which is equivalent to the socket bind program. And you can see there is all these other APIs like file listen, accept, send, receive are all like kind of equivalent. So this is one of the simple examples where we can see that simple TCP socket program can be converted into a Libfabric version. But this, the Libfabric version could be more generic enough that it could be, it could use different providers underneath. So next. So with in Libfabric, we have also enabled GPU communication. So on the left, you see the simple program flow for the GPUs could be like init. XE init is basically initialize the GPU device and then initialize the buffers with XE alloc buffer, ultimately doing ZE mem alloc, which is an Intel's GPU memory allocation call. And there could be init OFI, which actually registers the buffer with a NIC. So this is a generic program that can, right now we are showing that how it can be used with Intel GPUs, but this generic program can also cater to different type of devices. Imagine if there is a DPU, if there is a GPU from another vendor, it can easily plug into there. Next. So moving slightly towards the architectural outline of Libfabric, the bottom line that I was trying to make there was that Libfabric can provide those generic APIs that can address different hardware there. So its APIs are divided into 4 type of services. The control services are used for discovering the information about the underlying fabrics or the properties of those fabrics. The communication interfaces are the generic interfaces that could be used to set up the actual communication link. And then there are like data transfer services like FI send and FI receive that could be used for actual data transfers. And all of this is like generic for the applications above it or the middleware libraries above it. And it kind of hides everything at the bottom. And then there are completion services that would be used to report the results of submitted data transfers. Next. So these are like examples of different APIs. We had also presented this previously. So you can see there are examples of data transfer data transfer APIs like FI send, FI receive, FI write message, send message and receive message. There are communication services like FI endpoint, which is nothing but a socket equivalent of creating an endpoint. And then there are like completion services which are used for getting notifications for completion of data or any other kind of events there. And next, I think Juhi will show you the examples. I mean, the live demo of. She will walk you through the code of the socket example and then equivalent Libfabric API example. We will also see a simple, quick code walk for the GPU applications, and she will demonstrate how the data gets transferred between host to device and device to device within a single node, or it could be like across different nodes there. So to conclude, what I want to say is Libfabric can just be that one generic interface that makes developers' lives very easy. And it also helps, like Dr. Panda said, it also helps different vendors, hardware vendors, to plug into that whole framework very easily by providing those hooks at the provider level, and also like hooks at the user level as well. So yeah, over to you, Juhi, for the demo.
Thank you, Rajalaxmi. So I'm going to demonstrate two examples here to show the difference between a regular TCP socket-based message exchange and message exchange using Libfabric. So this is a basic, simple TCP socket-based message exchanging application. So first we start with with creating a socket, and we assign this to a socket descriptor. After creating a socket, we go over and bind the socket to the server's the address and the port. So this is used. This is done using the bind API call. After binding, we listen for any incoming connections on that socket. So once there is any incoming connection, we will accept that connection using the accept API. So this is the socket address where we got this connection, and this is the address from where we received it. And we'll assign this to our separate socket descriptor. So after that, we are ready to receive the message from client. So we'll do that using the receive API. And once we have that message, we also want to send an acknowledgement to the client that we got its message. So we will send an acknowledgement message with the send API. So for the client side of things, we are creating a socket again and assigning it to the socket descriptor, and then sending a connection request using the connect API on that socket descriptor. So after we are connected to the server, we'll send our message using the send API, and then the server is also going to send an acknowledgement message. So we'll receive that using the receive API. So once this data transfer is finished, we can go ahead and close our socket. So we'll use the close API and close the client and server sockets. So let's see this example live. I have the setup over here. So this is the server that has started. A socket was created, and we have bind the socket to our address, and we're listening for incoming connections. Now on the other side, I will run the client. So the socket has been created here, and we have connected successfully with the server. So let's say we want to say that okay, so our message was sent successfully, and the server also sent us an acknowledgement message. So this is a basic TCP program. Now let's say we want to do something similar using Libfabrics. So this is a program that shows how we can program a simple messaging application using Libfabric APIs. So in any Libfabric application, the first call to happen is FI alloc info call. This call will request for specific features or specific qualities that are required from the provider by this application. So we'll use the FI alloc info call, and we'll assign all of those to the hints structure. So this is an FI info type of structure, and we'll store all the features in this structure. Next, we'll ask for a message type of endpoint. So endpoint is similar to sockets. So it means that we want to have a message type of a socket to do the message exchange. And we'll ask for FI message capabilities. So again, because this is a messaging application, we are requesting for these capabilities. And we'll request for the TCP provider and request for the FI sock adder in type of addressing format because there is IPv4 addresses here. And lastly, we'll request for FI delivery complete. So this is a flag that we'll set. This just means that the completions won't be generated until client has finished sending its messages. Otherwise, the server might not receive its message. So after setting all of these features and hints, we'll go ahead and start our server. So for any server or client to start, the first call is FI get info call. This call is used to query Libfabric for all the available fabrics or providers available on the node. So we'll get a list of all the fabrics and everything available in the FI info struct, and we'll choose the first one for our application. Next, we'll open up a fabric with FI fabric call. So a fabric can mostly be viewed as a container object by an application, and a fabric needs to be opened before any other resources can be allocated to the application. Next, we'll open an event queue with a FIEQ open call. So this event queues are bound to the fabric, and event queues are basically used for connection management requests handling. So whenever there is a connection or like a connect or accept event that occurs, we'll store that event or log those events in the event queue. Next, we'll open up a passive endpoint. So passive endpoints are associated with the fabric, and this allows an application to listen for a connection coming into the connection request coming into the application or the server, and we can listen to multiple connection requests coming in multiple domains. So we will use a passive endpoint here to track our connection requests. So after opening up this endpoint, we will bind this endpoint to the event queue, and then we'll listen on this endpoint for any incoming request with FI listen call. So this is a continuation of the server. Once we are listening on the socket, once we are listening on the endpoint, we'll read the event queue to drive progress. This is because we are waiting for any connection event to be logged in, and once there is a connection event that is logged into the event queue, we'll start our domain with FI domain. So domain can be identified as a set of resources that can be grouped together or used together. It creates a boundary for associating resources together. Then we'll bind the domain with the event queue, and we'll open a completion queue. So completion queues log completion data transfer completion events like send or receive events. Next, we'll open up the endpoint. So this is an active type of endpoint. This will be the actual, or we can consider this as an actual socket, similar to sockets. So this is where our data transfer will happen. Now, the endpoint that we opened earlier, that was a passive endpoint, and that basically is just for connection management requests. So once we open an endpoint, we'll bind it to the completion queue and the event queue, and then we'll enable the endpoint. So after enabling, we know that our server is now ready to accept any data coming in or connections coming in. And once there's a connection, we'll accept that with FI accept call, and read the event queue for driving progress, because now we know that there is somebody who's going to write into the event queue, and we'll have to read that. So for that, we have the FIEQ as read call over here. So this is the server part of the details. After that, we'll start the client. So along like similar to the server, the client will also start with the FI get info call and get all the available fabrics and resource details into the infrastructure over here. And we'll select the first one. So we'll open the FI fabric again over here, with FI fabric call, and then open the event queue and domain, and then the completion queue. So this part is quite similar to how the server was initialized. Next, we open the endpoint with FI endpoint. So this is the client socket, and like similar to how the client opens a socket in the TCP example. Next, we bind this endpoint to the completion queue and the event queue, and then we enable the endpoint. So once it is enabled, it is ready to send out the data. So after that, we'll send a connection request on the endpoint into the destination address. So this is the server's address. So we'll send a connection request here, and on the other side, the server will accept it and log into the event queue. So we'll read the event queue over here, we'll read the event queue over here to see if the server has accepted our connection or not. And once we know that the server has accepted, we are ready for data transfer. So since this is done, now we'll go ahead and run the data transfer. So for the server, it will post a receive buffer with the with fi send call. So that is over here, fi receive call. So fi receive is basically for the server to receive a message. This call will require the endpoint, the buffer where we want to store the message. This endpoint is basically where the message will come in. This is the buffer where we'll store the message, and this is the address. So this address, since you're not mentioned what address it is, it can get a message from any client. So after that, we'll read for the completion queue. So once the server receives a message, it will receive a completion event into the completion queue, and we'll read for it. So this FIE again is an error return code. So this means that either the endpoint is not initialized or the client has not yet sent a message. So once we know that there is a completion, we'll go ahead and read the completion queue. So this is the comp variable is where we'll get our completion flags. And for the server, if FI receive is received, this means that the server has received a message, and it will say that I received a message. And similarly, for the client side, it is going to post a send buffer. So this post send buffer is basically an FI send call, and this means that we will send a message to this endpoint, EP endpoint, and to FI adder. This FI adder is the address of the server, and we'll read for the completion queue to drive progress here as well. And once we have received a completion event into the CQ, we'll read for the flags, and for the client, FI send is the flag that we'll receive, and it will say that my message got sent. So this is how the data is exchanged between the server and client using Libfabric APIs. And since we have finished up with our message transfer, we can go ahead and do a cleanup of all the resources that we have used. So the cleanup call is basically similar to the close call that we saw in the TCP socket example. So here, instead of close, we have FI close. This will close all of the resources properly. So first we'll start with the endpoint, then we'll close the passive endpoint, then you close the completion queue, domain, EQ, fabric, and the last thing we'll do is to free any of the structures that we use. So we use the FI info type of structures to populate the data from the fabrics, from the FI alloc info call that we had. So we're free of those structures, and then we are ready to go. So this is how the messaging application is done using Libfabric APIs. And now we can run this application. So this is the server. We have started the server, and on this side, I will start the client. So as we can see, the server has posted a buffer and is waiting for a message from the client. On the other side, the client has connected to the server and is ready to send a message. So once the message gets sent, it will receive the FI send completion flag into its completion queue, and then it will say that my message was sent. And on the server side, once server gets a completion flag of FI receive into its completion queue, it will say that it has received a message, and it will print out what message it has got. So this is how we program a simple messaging application using Libfabric. Okay, so this slide is basically to reiterate what we just saw in the examples. This is the same diagram, and the purpose is to show that we did a like we wrote a messaging application using sockets and Libfabric message endpoint, but ultimately it's doing the same thing. So next I will explain GPU data transfer using DMA-buff IBV APIs. And on the other hand, we'll also see how we can program a GPU data transfer application using the Libfabric APIs. So on the left side here, I have the DMA-buff IBV API example. So we'll go over the left section first. So these tests check the functionality or performance of DMA-buff based GPU RDMA mechanism. They use level 0 APIs to allocate buffer from the device memory, get DMA buff handle, and perform some device memory related operations. The IBV API example is a verbs test that measures bandwidth of RDMA operations. It runs in a client server mode. It has options to choose buffer location, test type, device units, NIC units, message size, and the number of iterations per message size. So we could do a write test, a read test, a send or receive test, and allocate buffers on either host memory or device memory. We will compare both the examples and run both to see how fast the data is transferred. So for the verbs example, prior to socket connection, there are a few parameters that are set, like the provider, where will buffers be allocated, message sizes, number of GPU devices, test type, etc. And after that, we go to the connect TCP, which will set up our socket connection between the client and server. And this is basically using the bind, listen, connect, and accept calls that we saw with the socket example. So after a socket connection, we initialize the buffers with init buff. So here we allocate buffers to the specified location on specified GPU using level 0 APIs like ZEMM alloc host, ZEMM alloc device to allocate memories on host and device and to allocate memory or buffer space, and initialize the buffers with level 0 APIs like Z command list append memory and Z command list reset. So once the buffers are allocated and initialized, we initialize the IB devices using init IB, and we get the list of GPU devices available on the node, and then initialize the devices where we open each device with IBV open device call. Allocate protection domains with IBV allocate PD call, create completion queues with IBV create CQ call, and create queue pairs with IBV create QP call. So this is the way we set up our fabric. Once this is done, we sync both the ends using sync TCP. So this is where we do a dummy data transfer to check that both the ends are ready for further operations. So now that we have our client and server setup, we will do the data transfer with run RDMA test, which ultimately is executing IBV post send verbs call. So IBV post send call is it posts a list of work requests to a send queue, and once this call returns, we poll the completion queue and check for completions. So now that we have transferred data from one memory location to another memory location and have the data on the destination side buffer, the last step is to tear down the fabric, and this is where we free all the resources, where we destroy the queue pair, the completion queues, the memory regions, or deallocate the memory regions, protection domains, and close all the devices. Then we free the buffers with free buff call, and then we close the socket with a close call. So this is how we do GPU data transfer using DMA-buff verbs APIs. So let me go ahead and show that example. So this is the dummy example that we have created, and with -m we specify where we want to allocate our memory region, or where we want to allocate the buffer space. So here I'm allocating it on the host memory, and on the other side as well, I will be allocating on the host memory. And we'll do a write test. So and we'll specify a message size. So since this is a dummy example, we'll just do a 1 byte memory or data transfer. So let's run this. So as you can see, we have transferred 1 byte of data here. This is using IB devices. Now let's go ahead and look at the Libfabric example. Okay, so on the right side here, I have the Libfabric API example where we'll use Libfabric APIs to do the GPU data transfer. Now, most of the process here is similar to the left side. The socket connection and initialization of the buffer is similar to the IBV example. Now, instead of init IB, here we initialize Libfabric resources. And Libfabric initialization is similar to what we saw earlier in the message example with the message endpoint transfer. So here as well, we will start with the fi alloc info call and set the hints with that. Then move to fi get info, open a fabric with fi fabric, open a domain with fi domain, set up event queues, completion queues, and then create an endpoint, create memory regions, and register those on the type of memory that we want to register on. So after initializing Libfabric, we are ready to start the test with the run test. Now, here you will notice that we are using Libfabric data transfer APIs for data exchange. So if we are doing a read type of test, then we would use the FI read message call, which is a remote memory access operation. It will read the data from remote buffer into the local buffer, or read the data from the client buffer into the server buffer. Whereas if the test type is write, then we use FI write message Libfabric API, which is also a remote memory call, remote memory access call. This call will write the data from client buffer into the server buffer. So once this data exchange is over, we start the process of fabric teardown. This process is also similar to how we clean up the resources in the message example. So we use FI close call to close all the resources like the endpoint, fabric, domain, event queue, completion queue. And then finally, we free the hint structure.
Right.
Lastly,
So, yeah, go ahead.
sorry, I was just finishing up saying that lastly, we free the buffers with free buff and then close the socket.
Right. So I think we are trying to focus two things here. One is the memory allocation on any type of devices. It could be GPU, it could be any other type of device, and it could be from any vendor. It could be Intel GPU, it could be any other vendor GPU. So that is one part. That is allocation of memory part. The other part is like the transfer of the data that could be done with the generic APIs in the Libfabric. So if you see here, init buff that is done on the Libfabric program, it ultimately right now, since we are using Intel GPU, it will ultimately go into the API call chain and call xealloc buffer, which will ultimately call a level 0 API called as ZE mem alloc device, which will allocate the buffer on the GPU memory. And then there is a init OFI call on the right hand side, you can see that will ultimately initialize the NIC. It will ultimately call FI MR reg ATTR, which will register the buffers with the NIC. So On the left side, if you have to write a program for each provider, then it will be like on the left side part here, wherein this is an example for verbs provider. You will have to write it for each and every provider, and then there could be different type of APIs for different GPU providers, or like different GPU drivers can expose different APIs. But on the right hand side, we can achieve both the things with this one Libfabric program. Yeah, we can go into demo, Julie.
Okay. So I'll go ahead and show how we do this example. So I have a dummy example for this as well over here. And instead of the RDMA bandwidth XC, we have FI RDMA bandwidth XC. To note that this is a Libfabric example. Similar to the previous example, we'll use the host memory to allocate our buffer. And on this side, now let's do a read example this time. So we can send 1 byte of data. So this is this is how we program the FIRDMA bandwidth example, and we just transfer data using the GPUs. And as you can see, this is using the OFI device. Now,
Juhi, this is host to host transfer. I think we were next. You are going to show the device one,
yeah,
right?
I
Yeah,
was
yeah.
just doing that.
Yeah.
So instead of so we can also do a host to device or a device to host transfer as well. So next I'm going to show a host to device transfer. So instead of the host here, we can say that we want to allocate buffer space onto the device memory. And here, let's say we just want to do we just want to use the host memory, and let's try a write example. Sorry. Okay. So as you can see here, we transferred data from host to device with the write test. So this means that the host would write data from the device memory into its own memory. And again, here we are using the OFI device. So as I said, we can do multiple tests over here. We can also do device to device memory transfer. So this is how we program the Libfabric based GPU data transfer. So here I have some more information about Libfabric. Please go ahead and check these links. We have some examples over here as well. These are the same as I presented, and we also have the examples that I presented last year. So this brings us to an end of this tutorial. Rajalaxmi, if you have any last thoughts.
No, I think yeah, I think this is about it. If there are any questions, you can we'll wait for a minute here. You can post it in the chat. I know Amanda is out, so we are moderating ourselves here. Or
Yeah.
you can post on the Slack channel as well.
Do you see any questions in the chat?
No,
I'm not sure.
I don't see any questions in the chat. So I think we are good. Please feel free to reach out to us either on the Slack channel, or you can email us if you need more details and examples. Thank you so much, and have a wonderful rest of your evening. Bye.
Thank you. Thank you all for attending.